further ado,
All right. First of all, I honestly don't have much idea what I'm doing here. Joe asked me Friday afternoon to do this, and I said, no, I'm going home for the weekend. We're going to spend a pleasant weekend with my wife. We're going to go to the theater. I'll have absolutely no time to prepare. He said, it doesn't matter for these people. Don't worry about it. They don't matter. So, number one, I'm unprepared. Number two, I don't know who I'm speaking to. I see in the audience a bunch of my black holy friends, but I assume I'm going to ignore them completely. I was told there's maybe a biologist or two here. Is that right? And an astrophysicist. I don't know. Okay, so it's a mixed group, which is fine. That's good. And the last thing is, quite frankly, I thought we would be sitting around a table. He said a lunch thing, and I thought we'd be sitting around a table like we do at Stanford in a civilized way, and one person stands up and talks while the others eat lunch. I did not expect to be in an auditorium giving a lecture. So let's start, and it would be very helpful if you ask questions, because I'm like a wind-up doll. I wind up with questions, and then I like to answer them. But I'm going to begin trying to tell you why my friends and I are joined together here to explore a set of questions which has come up, I would say about black holes, but to say it's about black holes is much too narrow. It's much too narrow. What we're addressing is a problem which has been around for close to 100 years. The problem of how to synthesize or how to put together quantum mechanics and gravity. It's been for a good number of years, there was very little. The subject kind of exploded with the advent of Hawking's and Bekenstein's discovery of black hole thermodynamics. And I'm going to tell you a little about that. But I'm also going to try to tell you exactly why we're here, to explore a certain paradox. Paradoxes are very interesting. In fact, it's generally the way forward when you simply don't have anything else, when you have no experiments, when you have no empirical data, but you have a set of concepts, and the set of concepts clash. When the set of concepts clash, then you may have something to learn. Light traveling at the speed of light in every frame of reference, atoms not decaying down to the point where the electron falls into the nucleus, quarks not getting out of the proton and neutron, the cosmological constant being 123 orders of magnitude smaller than the start of life, how life forms. All these are paradoxes. Sometimes they're really clashes of principle, and that's when we stand to learn something really new and really exciting. That's hopefully what's going on now. Now, whether we'll be smart enough to crack it, I don't know. Whether we'll all discover perhaps that we were making a foolish error. Whether we would discover that Joe Polchinski was making a foolish error. I don't know. I don't think so. No, I don't think so. I think there's a big paradox. The big paradox will get solved. My guess is the solution will be that we were going on the right track before the paradox, but we were missing something enormous, some big, huge piece of the story, and that we have a good chance to learn it now. So what is it all about? Well, it's about quantum gravity. And the first thing I want to say is that you should not think of quantum gravity as being quantizing gravity. Quantizing is an operation that we do on known classical theories. We take a known classical theory, we invent some hocus pocus called Poisson brackets, and Poisson brackets, a formula. There's a rule, there's a set of rules. Dirac invented them. That has gotten us nowhere with quantum gravity. It's gotten us almost nowhere at all. And it's probably because quantum mechanics and gravity are linked in a much, much tighter way, joined at the hip, as they say, in a way that doesn't allow us to separate them. Of course, we can study classical gravity. There's no doubt about that. But some of us are beginning to feel, I think probably everybody here, that quantum mechanics and gravity are joined in a much, much deeper way, in an inseparable kind of way, and that it doesn't really make sense to take the classical theory and just apply to it the standard rules. Well, if the standard rules aren't helpful, and if there's no experimental data, all we can do is explore these paradoxes which come up now and then. Most of the paradoxes have been about black holes. Why black holes? What does a black hole have to do with quantum mechanics anyway? My friend, who I hardly know, in fact, I don't think I really know him anymore. I used to know him in 1976. Freeman Dyson thinks that it's a complete waste of time to think about quantum mechanics and gravity in the same breath. Quantum mechanics is, of course, applicable for very tiny things. Gravity is applicable for very big things. Why mix the two all together? And of course, the answer is it's just intolerable to have two theories which seem to clash and simply don't want to fit together. It's intolerable for curious people, for people with a kind of itch that want to put things together into a neat framework, a neat universal framework. And so, we're just obsessed with the question because we're curious about it. That's the only reason, as far as I can tell. I don't think quantum gravity is going to solve the climate change problem or the cancer problem or anything else. We do it because we're curious about it. Okay, now, why black holes? Black holes happen to be the place where quantum mechanics and gravity come together. Despite the fact that black holes are very big and very heavy, the structure of the way that they contain information, the way that they interact with the rest of the world through radiation and other things is highly quantum mechanical. And so black holes seem to be the natural doorway, the place where we get really surprising paradoxes from that we can explore in hopes to learn more about the connection between quantum mechanics and gravity. That's the point. All right, so let me begin about black holes with some tension that was already there in the classical theory of black holes. It's not a real paradox, but it's a bit of tension. So let me show you what the tension is. The tension has to do with the difference of descriptions from outside the black hole and from somebody falling into a black hole. Here's a black hole. What I've drawn is the horizon of the black hole. And the horizon of the black hole is a place from which, on the outside, somebody can shoot radiation or something else can shoot things out which will escape. And the inside is the place that gravity is so strong that anything you shoot either in or out will wind up at some nasty singularity at the center. We don't need to be more precise about it than that. It's a dividing line. It's a point of no return. Anything that falls through is trapped. Anything that is outside has a chance to escape. Now, the property of clocks and measuring rods get very distorted near a horizon in the following way. You probably all know this, but let me just remind you that if an object is falling into a black hole, from the perspective of the outside, from the point of view of coordinates which are built to describe the outside of the black hole, what happens is the object asymptotically slowly approaches the horizon. Now, this is because clocks slow down in a funny way near the horizon. Nothing is observable about that slowing down to the observer falling in. The reason is his clock slowed down, his heartbeat slows down, every internal clock that he has slows down. So he sees nothing, but his comparison with outside clocks far away watching him is such that, first of all, he asymptotically slower and slower and slower and slower approaches the horizon. And at the same time, Lorentz contraction takes place, So after a long time, this blob over here, this is all classical now, becomes a thin little blob asymptotically approaching closer and closer to the horizon. In fact, not only will that observer be, I was going to say stretched out. Stretched out is not quite the right word classically, just plastered against the horizon like this, but everything that ever fell in to make the black hole has exactly the same property. It's all contained in infinitely thin, well, not infinitely thin, but progressively thinner and thinner shells that approach the horizon asymptotically, never quite getting there. It takes an infinite amount of time from the perspective of the outside observer for anything to get to the horizon. So in a sense, nothing ever gets there. And our description of the black hole from the outside should be then a shell called the horizon, inside of which there is nothing that will ever be important to us, because from our perspective, nothing ever fell through. And all the matter that ever fell onto the horizon is in this progressively thinner and thinner, it's a kind of sediment, sedimentary structure that just falls toward the horizon, never quite getting there. Now, there are two things which are infinite. First, for a classical black hole, the first is the time that it takes for anything to get to the black hole surface. And the second is the amount of information that you can hide in this thin sedimentary structure that just approaches the horizon. There is no limit classically on how much structure of this kind you can have at the horizon of a black hole. Structure, I mean information, bits of information. Bits of information in classical physics can be encoded in arbitrarily weak signals of arbitrarily low frequency or energy, arbitrarily low energy. And so these weak signals can carry any number of bits of information. And so the hidden information at the horizon of a black hole can be infinite in classical physics. Hidden information has another word. The word is entropy. So in classical physics, some people sometimes think that Bekenstein discovered that black holes have entropy. Not at all. What he discovered is that they don't have too much entropy, that the amount of entropy that they have is in fact finite. So we'll come to that in a moment. So those two things that are infinite, the time that it takes to fall through the horizon from the outside, and the amount of information that can be stored on the horizon. For those people who know about black holes, this is familiar and a standard story. For those people who don't know anything about relativity, what I'm about to say next will be useless. But for those people who are somewhere in between, let me draw you a diagram to show you how it is consistent that it can take a finite amount of time to fall through the horizon for the infalling observer, and yet an infinite amount of time as seen from the outside. Did I neglect to say, I don't remember if I said, that the amount of proper time that it takes something to fall through is quite finite. That's the tension. A finite amount of time that the infalling observer experiences falling through the horizon, and an infinite amount of time as seen from the outside. All right, so it's a simple picture that will help. That's Minkowski space. Why am I interested in Minkowski space? Because Einstein taught us the first thing you want to do when you want to understand gravity is understand acceleration. Understand physics in flat space in an accelerated coordinate system. An accelerated coordinate system in Minkowski space looks like this. These are the lines of constant position, and the lines of constant time look like this. It's a kind of hyperbolic structure. This is an infalling reference frame. Time goes this way, space goes this way, and those are uniformly accelerated frame of reference. Now imagine, this is t equals 0, this is t equals 1, this is t equals 2, t equals 3, dot, 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 until you get up to this line, and that's t equals infinity. A little bit odd. Now somebody falls through, or no, somebody moves along this direction here. There's no horizon here. There's no black hole here. This is just flat space-time. But how long does it take for this blue observer here to pass the light cone over here? Well, from the point of view of his own internal clocks, it's clear. It's a finite amount of proper time. The length of this line is finite. Nothing special. This observer falling through doesn't care about this odd set of coordinates. On the other hand, somebody standing outside, and staying outside involves accelerating. You cannot stay to the left of this light cone without accelerating. In the same way that I cannot stand on the floor of this room without accelerating. Accelerating means experience and acceleration. So Einstein said, if you want to understand gravity, understand acceleration. Here, we're trying to understand acceleration, and we have a funny situation. If you stay outside this light cone and watch somebody falling through, it takes an infinite amount of time. On the other hand, there's nothing infinite about the perceptions of a person falling through. So both are true. Both are true. Classically, it was never regarded as a tremendous paradox. It was just regarded as a curiosity. This is the structure of a black hole geometry very near the horizon. You don't have to know very much. All you have to know is that the region back here maps to the region behind the horizon. And notice that somebody who's out here can never send a signal to this side of this light cone. That's equivalent to saying that something that falls through the horizon can never send a signal out. Any signal winds up going in and not out. All right, so that's the setup. Infinite time, finite time, infinite amount of information can be stored arbitrarily close to the horizon. All right, now, as I said, hidden information is called entropy. Well, I think it was in 1972 that Jacob Bekenstein asked a very fundamental question. Somehow nobody had asked it before. If a black hole can store an infinite amount of information that just keeps collecting and collecting and collecting, either think of it that way or falling into the black hole, either way, you'll have a situation which is somewhat like early quantum mechanics, or before, pre-quantum mechanics. In pre-quantum mechanics, the radiation field of a given amount of energy could contain an infinite amount of information. It was called the ultraviolet disaster. Because each mode of the radiation field, no matter what its frequency is, can store arbitrary amounts of entropy, what will happen classically is if you have some energy contained in radiation, it will just migrate more and more and more into the ultraviolet modes, where there's simply an infinite phase space to absorb the entropy, to contain the entropy. Same thing would happen here. Any amount of entropy that's in space here will just get sucked more and more and more into the black hole. And if you didn't account for the fact that the black hole itself had entropy, you would conclude that entropy was lost to the world. It's not lost to the world. It's absorbed into these infinitely thin layers here, and it can't get out, not without getting very close to the speed of light. But Bekenstein didn't like that. It didn't feel right. He suspected that somehow black holes are like anything else and have a finite entropy. I'm going to take you through Bekenstein's argument, because if I don't teach you anything else, this is really one of the most beautiful Gedanken pieces of physics that I know of. And it can be taught, easily taught to a physicist who doesn't know about black holes. In fact, it can be taught to a high school student that doesn't know calculus. So I don't see any high school students that don't know calculus, but you might take this home and explain it to your teenager. Why do black holes have a finite entropy, and how much is the entropy? And here's the way the argument goes. What we're going to do is we're going to build up a black hole from scratch by dropping in particle by particle by particle and asking, after we've built up the black hole to a certain size, what's the number of particles that we need to send in? Why particles? In a simple situation, a single particle contains one bit of information. It's either there or it's not there. Well, that's not right. Wait a minute, that's not right. If I want to build up a black hole by sending in bit by bit, and a bit means one piece of information, I cannot do it with high frequency or localized photons. The reason is a localized photon has more information in it than just the fact that it's either there or not there. Namely, it has information about where it might fall into the horizon. So what you want to do to send in one bit of information into a black hole is to send it in the form of a photon whose wavelength is so long that you can't distinguish where it passed through the horizon. Okay, so let me write some simple formulas on the blackboard, and you'll get the idea because it's very simple. The first formula is the formula for the radius of the black hole in terms of its mass. That's equal to the Schwarzschild radius, and many of you have seen it, twice the mass times Newton's constant divided by c squared. That's why black holes are so small. G is small, c is big. A black hole for a given mass, the mass of a black hole the size of a black hole, the mass of the Earth, would be about as big as a peanut. That's what the c's are doing here and the small g. Okay, so that's one formula. Next formula, I'm going to imagine building up the black hole from a small, tiny little thing by throwing in one particle, one photon at a time, one massless photon at a time, but a photon whose wavelength is about equal to r at that time. Why? Because I don't want that photon to have any information about it other than the fact that it fell into the black hole. Okay, so the wavelength is equal to r. How much energy does that add to the black hole? Well, the energy of a photon is, let's call it delta E, the change in the energy. That's h bar c over lambda. Now notice I'm doing quantum mechanics now. H bar has come into it. The change in the energy of the black hole due to sending one bit of information in is h bar c over lambda, where lambda is equal to r. What about the change in the mass of the black hole? Well, we use E equals mc squared. So the change in the mass of the black hole will have two additional powers of c downstairs. And the change in the mass is h bar over rc. Okay, next step. Let's compute the change in the radius of the black hole. We know the change in the mass. So the change in the radius due to dropping in one photon, the change in the radius is going to be 2g over c squared times h bar over rc. Haven't even used any calculus yet, and I'm not going to. That's the change in the radius of the black hole, adding one bit of information to it. Namely, a photon was either there or not there. Okay, let me clean it up. There's a c cubed downstairs, and there's an r downstairs. I want to get the r out of the right-hand side. That's easy to do. You just multiply by r. But r times delta r is a familiar thing. It's the change in r squared, which is the change in the area of the horizon. What's that? Oh! You're right. Somebody's very quick. Yes, indeed. You need some calculus to know that r delta r is delta of the area. Now, I have set everything under the sun equal to 1 except the important quantity. Well, I said 2 pi, 4 pi, I don't know. The change in the area, notice what it says. The change in the area of the black hole due to one bit of information is a universal constant. It does not depend on the radius of the black hole, it doesn't depend on its mass. Each time you add one bit, you add another unit of area to the size of the black hole, to the horizon area. You can write this a different way. You can say the number of bits that it took to make a black hole of radius r, and I'm going to call that the entropy of the black hole. It's the number of hidden bits of information. That, we'll call it S for entropy. I don't know how S ever got to be entropy, but the entropy of the black hole, the number of bits of formation, is equal to the area, the final area, since each bit increases the area by this much, then by this much, then the entropy of the black hole is the area measured in this unit. The 2 is not important here. Actually, the 2 is important, and it's not 2, but h bar g c cubed. Strictly speaking, there's a 4 downstairs. Not coming from this argument, coming from Hawking's very sophisticated argument, but this is the basic idea. The entropy of a black hole, the maximum number of bits of information that you can hide in it. And sending in photon by photon this way does maximize the information that you can get in there. The maximum amount of information, or the entropy of the black hole, is the area in a unit, which is the Planck unit. 10 to the minus 66 square centimeters, a very small unit of area. That was the discovery of Bekenstein, and later Hawking put some additional substance into it. In fact, what Hawking, I wasn't around. I was certainly around at that time. I was almost an old man at that time, but I wasn't around Cambridge when this was done, or Princeton. So I don't know exactly who figured out what and when and where. But once a thing has both entropy and energy is its mass, mc squared, it has both entropy and mass, it's going to have temperature. I'll just remind you, dE equals temperature ds. And if you know how the energy changes as a function of entropy, or how the entropy changes as a function of energy, then you know the temperature. And what you find from a little bit of thermodynamics is another equation, the Hawking temperature, T is equal to 1 over 8 pi, and now I'm actually putting in numbers, 8 pi, h bar, and now I've forgotten where the C's go. I don't remember. Anybody remember? It's just dimensional analysis. So if you're like me, the speed of light is equal to 1 over h bar g, m, mass of the black hole. The temperature goes down with mass, down with energy. That's negative specific heat.
You want a G in there? You want a G in there? G
Yes, I do. Thank you. G. Good. The important thing to note, well, all of it is important, but the h bar is in the denominator. In other words, in the classical limit, the entropy, or the amount, that's the storage capacity of the black hole to hide information, becomes infinite. But quantum mechanics, as in many other contexts, makes things which classically are infinite, makes them finite. Notice also that the temperature is a quantum effect. The temperature would be 0 in classical physics, and the entropy infinite. That is the description of a black hole from the outside. From the outside, a black hole is just an object with a certain energy, a certain entropy, and because it has a temperature, it radiates. It radiates black body radiation. Unlike the sun, which radiates with wavelengths vastly smaller than the sun. So you could use sunlight to resolve the sun in the sky. The black hole radiates with wavelengths comparable to the whole size of the black hole. So if you try to look at a black hole with its own radiation, it looks pretty fuzzy. That's not why this thing is called fuzz or fire, is it? I didn't, it's not, I don't think. No, I don't think so. Okay. Okay. That's the description from outside. Just an ordinary thing, a warm, cooling thing. Just for some numbers, incidentally, the entropy of a solar mass black hole, I think, is somewhere up near 10 to the 70th. I don't remember exactly. 10 to the 68th. So that's big. You can't think of anything else in nature that's the size of a black hole that would have anything comparable. Its temperature is very small. I don't know, 10 to the minus 8 degrees or something like that. And it's an odd object. It has some other amazing properties. It thermalizes faster than anything else, but that's okay. The central question is, if this is what, let's think about it for a moment. What it's telling us is that this infinitely thin sediment and its infinite capacity to hold information was not right. Somehow there's a finite capacity to hold information. And one way of thinking about it is to say that you cannot store anything on a vertical scale here smaller than the Planck length. That's basically what it comes down to. There's a fundamental length on the horizon or just adjacent to the horizon, and information cannot be squeezed smaller than that. That's what this says. Now, of course, another very odd thing is in almost every context where we think about entropy, entropy in this room is proportional to the volume of the room, not the area of the room. And that's kind of telling us somehow that there's nothing inside the black hole. Okay. That there's just nothing inside the black hole because the entropy is proportional to its area. On the other hand, classical black hole physics also tells us that it's meaningful for somebody to fall through the horizon. It takes a finite proper time, and so now we are getting into paradox land. The exterior of the black hole has a brick wall or a shell that nothing can penetrate through it, on the one hand. Everything gets stuck at this. This is called the stretched horizon, incidentally. Stretched because it's a little bit bigger than the horizon. It's called the stretched horizon. And the picture is that a black hole is just a hollow sphere with absolutely nothing in it, because its entropy is proportional to its surface area, with some kind of microscopic degrees of freedom. It could be string theory, it could be fuzzballs, it could be who knows what it is, but some kind of microscopic structure. It's hot, it has temperature. Incidentally, you might think that it has low temperature. It doesn't. The photons which come out here become redshifted as they go out. That's why the temperature is so low as seen from far away. But the temperature close by, that same temperature is blue shifted, and it's enormously hot. So that's our picture of the black hole from the exterior. It took a long time to develop it. It took a long time to develop it and get the ideas, what I think is correct. But in all of the studies of black holes, in the black hole information and so forth, in the last 25 years or 20 years or so forth, the emphasis was on this picture from the outside. And people forgot to ask, wait a minute, how do we describe the infalling observer in this same picture? The infalling observer, one possibility is that the black hole really is just a hollow thing with nothing in it, not even any space-time in it, in which case nothing could penetrate it. That's one answer. But that's not very satisfying for the simple reason that Einstein's theory of gravity and this picture here certainly suggest that a freely falling observer would take a finite time to go through. So the puzzle arose of how to reconcile the idea that things can be on the inside of the black hole, planets, stars, whatever, if the black hole is big enough. Things can be in there from the point of view of an observer falling through the horizon, with the picture from outside that it's just this hollow thing with microphysics on the boundaries. That led to an idea, which I think most of the people who work in this subject accept as correct, an idea called the holographic principle. I'm just going to state it very, very briefly. The basic idea is that this boundary structure out here functions as something like a hologram. I'm not going to try to do better than that for this audience now. Where's Juan? Is Juan Maldacena here? No, he knows all this. He put this in a very, very sharp context. The idea had been around for a few years before he got his hands on it, but he really nailed it and got a very clear idea of it. But the idea is, yes, there are things on the inside, but their relationship to this structure, which is holding all the information that ever fell onto the black hole, is, roughly speaking, this is a metaphor, it's not a theory, the metaphor of the hologram. The information can either be thought of as being stored on the film, or the film can just be thought of as a representation of the three-dimensional reality, and I'm not going to go into that any deeper than that, because that would take us all day. Okay, so that's the picture as it was roughly a year and a half ago. Not quite the whole story. In addition, this material, or whatever it is, being hot, can also radiate. And in the process of radiating, it loses energy, and the whole thing gets smaller and smaller until it evaporates. That's the amazing evaporating black hole. Okay. So let's come to the quantum mechanics of this and what we think what the dilemma is, what the conflict of principle is. The first thing is to put yourself in an infalling frame of reference that's just passing through the horizon. There's one thing that quantum mechanics requires of the description of empty space. The infalling observer, according to this theory, just experiences empty space, nothing more. Falls through, experiences an empty space, and empty space has a property, it's called entanglement. It's quantum entanglement. If you don't know about quantum entanglement, you can read Dennis Overby's description of it. It's as good as anything else. But whatever quantum entanglement is, it's a relationship between pairs of systems. It's not a relationship that has to be there, but it's a relationship between pairs of systems that can be realized, a pair of electrons, just a pair of regions of space, which says that those regions are highly correlated, but in a deeply quantum mechanical sense. I won't try to explain entanglement except to say that it's what Einstein called spooky action at a distance. It's not action at a distance, but it is spooky. And here's what vacuum quantum field theory, the theory of empty space, tells us. It tells us if somebody passes through, they should see the interior regions of space. Let's call them A. The Santa Barbarians have some notation which involves any number of twiddles and primes and stars, and it's very bad. And B. B, of course, is the obvious notation for zone. That's supposed to be a joke. A is the interior. So A for interior, B for zone, and why B is called the zone doesn't matter at all. The interior, just beyond the horizon, and the exterior, two regions of space, are highly entangled. I will represent that by drawing a line between them. There is no line between them, but they enjoy this property of entanglement between them. What entanglement means is that if you measured B, you could find out what you want to know about A. If you measure A, you can find out what you want to know about B. They're entangled. All that's fine. No problem there until the black hole starts evaporating. And as it evaporates, what happens is the entanglement between A and B, between the interior of the black hole and the near horizon region, the region just outside the horizon, gets replaced. Basically, these degrees of freedom go flying off. They go flying off into the radiation, and after the radiation has emitted, in particular after about half of it has been emitted, half the radiation that will ever be emitted, instead of A being entangled with B, A, the interior of the black hole, and B are entangled instead with the very, very distant Hawking radiation. The Hawking radiation is impossibly far from the black hole by the time the black hole is radiated. And so one is left in a dilemma. It looks like something awful has one more step. A has become entangled with the radiation far away. But now there's a famous quantum mechanical theorem. It's called the monogamy of entanglement. Two things, if you have three things, and two of them are entangled with each other, the third cannot be entangled with either. So now we have a puzzle. If in order to make sense out of this holographic picture of the interior of a black hole, we require, from the point of view of the inflowing observer, that A and B be entangled, but at the same time we discover that these degrees of freedom become entangled with very distant radiation, then the result is that the entanglement between B and A must be destroyed. That sounds like a disaster because the destruction of the entanglement between these two near regions here would really perturb the nature of the vacuum between the interior and the exterior very seriously. It would make it hot, it would make it very dangerous. It would imply that somebody falling through the horizon here would not see sensible physics there. They would see something awful. Yes, Stephen?
Did you really want to say that B was entangled with your radiation?
Both. I'm simplifying a little bit. No. Yeah, B becomes entangled with the radiation and can no longer be entangled with A, which really means it can't be entangled with a stretched horizon. But you know, let's keep it simple. So instead of this bond being there, entanglement of B with A, we have B with this thing out here, the Hawking radiation far away. As I said, that sounds like a terrible perturbation on the horizon of the black hole. Unless there is one possibility that information theoretically, in counting where bits of information are stored, unless the interior of the black hole is really encoded in the distant Hawking radiation. Then we will simply say B is entangled with the Hawking radiation, but the Hawking radiation is just another way of speaking about the stuff behind the horizon. That's called an A equals RB theory, and it stands for the interior being constructed somehow out of the radiation far away, which is entangled with B. Now, I won't try to explain that, except to indicate to you how absurd it is. What it's saying is that somehow the interior of the black hole is really being represented, a nearby black hole, you know, a black hole at in this room, that its interior would be represented in terms of degrees of freedom, which could be, I don't know how many times bigger than the universe far away. That doesn't sound reasonable. Nevertheless, I think it's true, I think it's where we're being driven, that a degree of delocalization, first of all, let me say this. Even the holographic principle was a delocalization of where information was. A thing which we all accept, the idea that the interior of a region is described by degrees of freedom on its boundary, that already is a degree of delocalization. But this is an extreme degree of delocalization, that the information describing Alice falling through the horizon over here is contained not on Alpha Centauri, not at the, much, much further away. Seems absurd. What's the resolution of this? After the black hole has become entangled with a very, very distant radiation? Well, one possible answer, to my mind, a clumsy, heavy-handed, brutal dumbbell idea, is the firewall idea. Now, the firewall idea is a misnomer. I don't think you should think there's some terrible fire just outside the horizon. I think the firewall idea really should be phrased by saying, once you disrupt the entanglement between B and A, then the right picture, according to the firewall enthusiasts, is that there just is no interior. The interior has been scooped up and put out here in the radiation, information theoretically. There is no interior. Somebody falling in just hits a blank wall, not a firewall, but a dead end. You're not burned, you're terminated. Right. Okay, but it doesn't matter. I mean, the idea, that's one resolution. Don Moroff seems to be the only person who truly believes this with any real intensity. Joe says things like, well, I don't really believe it, but all the evidence seems to be pointing in that direction, but I don't really believe it. And other people, myself, Juan Maldacena, the Verlinda brothers, I mean, these are really substantial people, very real heavyweights. They think the firewall is a crock. Okay? And I think the firewall is a crock. But damn it, we can't figure out what's wrong with Joe's argument.
Many people's argument.
Many people. Excuse me. That was a bad thing to say, right? It has been many people's argument. We think it's a crock, but we can't figure out exactly what's wrong with it. I myself suspect that there's something true to, and others think there's something correct about the idea that the distant Hawking radiation is information theoretically and holographically a description of the interior of the black hole, but there are other paradoxes. I have not explained the full ammunition that the firewall people have to bring to bear on this. They have a number of arguments. I think it was Feynman who said if you have more than one argument, they're probably bad because one argument. But in this case, I think the more arguments, the stronger the case is. And we don't know what's going on. There are different theories. I could tell you one of them has to do with wormholes. Some really nutcase people who believe in wormholes. Other people think that quantum error correction is important. They're also crazy. I belong to both groups. But my own guess is whether or not it's wormholes and quantum error correction. I don't really think it's these firewalls. That just seems a little bit too simple to me. My guess is we're going to learn something truly deep about the connection between quantum mechanics and gravity from this exercise. And I can't tell you what it is with any certainty right now, but it's exciting. It's exciting, it's interesting. One has the feeling that at any time some young person can come along, put his finger on it, and that it will really be some new perspective into the quantum mechanics of gravity that I think is unexpected. I talked longer than I expected to, actually. I was expecting to stop and field questions, so I can do that now for a little while until... Thank you.
Ninth question. What does it take for two quantities, two zones, what have you, to be entangled? What is the condition?
Well,
or not entangled?
Yeah. I'm not sure. Are you a biologist or a physicist?
No, astrophysicist.
Astrophysicist. So you learned a little bit of quantum mechanics, right? Okay.
Just a little.
that may have come out not the way I intended. All right. So systems have wave functions. Wave functions depend on the degrees of freedom of the system, and if you have a pair of systems, then the wave function depends on both variables. So it's a psi of, let's call them x and y, but these don't have to be coordinates, they're just two variables. An unentangled state is one which is a product, psi of x times phi of y. This is a state in which there are no correlations. Statistical independence, but quantum statistical independence between the two systems. Any state which is not of a product form is called entangled. Now, there are degrees of entanglement. How strongly are they entangled? Just a mild deviation from product would have a little bit of entanglement. There are situations which are extremely entangled. I won't write one down, but in which there's an enormous degree of correlation, so much so that anything you might want to know about one of them, you can look at something in the other one. Now, classical correlation is similar, but the difference is something like this. If I tell you that I have a probability distribution, you know what a probability distribution means. But you also, I think most people would say the following is true. If I know everything that can be known about a composite system, then I know everything that can be known about either of its parts. That's logic. I mean, how can you not mean that? Quantum entanglement is exactly the opposite. You can know everything that can be known about a composite system when it's in a highly entangled state and still have no knowledge whatever about the individual components. What you have a lot of knowledge about is the relationship and the correlation between the individual components. So quantum entanglement, everybody knows who invented quantum entanglement, right? I mean, it was Einstein. Who was he was extremely troubled by this idea that you could know everything about a system and know nothing about its parts. That, I think, if I had to guess what really bothered him and made him feel very uncomfortable with quantum mechanics, he called it that quantum mechanics could not identify elements of physical reality. I think what he meant was exactly this. You could know everything about a composite system and know nothing about its parts. So that's what entanglement means. And entanglement is entangling itself into theoretical physics now in a really major way. It's in statistical mechanics, it's in condensed matter physics, it's in black hole physics, it's all over the place. It'll probably get into cosmology at some point. It's an infection, the entanglement infection. And here is an entanglement disease that we are not yet understanding. Anyway, that's entanglement. Yes, Matthew.
I'm just trying. Question doesn't even make any sense. But could A and B disentangle?
That's very bad for the vacuum. It's a question of energy. If the Hamiltonian of the system favors entanglement, for example, a singlet state of a pair of electrons, then to break that entanglement costs energy. All right? To break the entanglement between A and B would necessarily heat the vacuum, or would necessarily increase the energy of the vacuum in between. If every single mode near the horizon, if the entanglements were all broken by this radiation, then You could call it a firewall, you could call it complete destruction of the nature of the horizon, but it would be brutal. It would be like taking a pair of electrons which like to be in a singlet state, like means it lowers their energy, and forcibly disentangle them would raise the energy. You raise the energy of every one of these, and that's a serious perturbation.
Does that assume you know the Hamiltonian on arbitrary short scales right on that far?
Well, we're not actually talking about arbitrarily small scales. Let's suppose we don't want to know whether there's a true Planckian firewall. We just want to know if when we pass through the horizon we will be scalded by hot water. Okay. Hot water is very close to or the temperature of hot water is practically the vacuum, but nevertheless it would burn you. Then we can be talking about things that are pretty well separated here, separated by a Compton wavelength associated with boiling water. So you can't get around this by saying, oh, look, this is all Planckian physics very close to the horizon. That won't do it for you. I don't know if that answered your question or not. Yeah.
You said that when bits of information fall into the black hole expands in certain extent. The area expands, radius expands. So when the black hole expands, the information already at the surface, what happened to them? Do they get swallowed into a black hole, or they expand with the horizon?
Well, okay. From the outside point of view, what happens when something falls into a black hole is, in an almost acausal way, I don't think it really is acausal, but the horizon expands a little bit, the stuff comes out to meet it, it falls in and mixes up with the stuff in the stretched horizon. That's the picture that is common these days. That it falls in, is absorbed into this hot stretched horizon, its bits absorbed into here, but through this holographic mapping, it's equivalent to something falling through the horizon. And I think we understand that a little bit. We don't understand that a lot, but we understand it reasonably well. It's what happens when all of the correlations and entanglements get transferred to the radiation going out that we don't understand.
Yes.
Yeah.
I have a question. I'm trying to understand the entanglement again.
This specific entanglement or entanglement in general?
Well, the case that you've drawn there. So
Yeah.
you have A and B on either
Yeah.
side of
Okay.
the horizon.
Yeah.
Are you starting in that state, or are you
Yeah.
starting prior
That's
and then falling in? Because
that's the state that you expect the black hole to settle down to after it's been formed.
let's consider a case where you have an entangled A and B just outside the horizon,
Outside the horizon. Yes.
outside the horizon,
Yes.
and then A falls in.
Uh-huh.
As far as B is concerned, the entanglement with A never ceases, right?
That's right.
And so, in that case,
Well, okay.
They could remain entangled,
Yeah,
right?
you do. If you have an entangled pair and you throw one in, you can think of it two ways. Both are equivalent. One way is to say the other member of the entangled pair gets smushed, or whatever the right word is, scrambled is the technical term. No, it is. Scrambled is, I kid you not, scrambled is a technical term. Right, that bit gets scrambled into the stretched horizon here and gets absorbed into the black hole. But then what you say is that this particle over here has become entangled with the black hole. It's become entangled with the stretched horizon. Another picture of the same thing is that it's entangled with a particle which falls inside. Incidentally, there's a neat analogy for this, which is due to Juan Maldacena. Almost everything in our subject these days is due to Juan Maldacena. Imagine you have a mirror. It's a spherical mirror, and you have a charge out here. I'm thinking quantum mechanics, but it's a quantum mechanical charge. Then the charge develops an image charge on the inside. Now, there's no real charge on the inside. What is really going on? What's really going on is the charges in the mirror get readjusted. They get readjusted and simulate a charge in the interior. You can think about the quantum mechanics of this particle here Well, again, I was thinking, of course, of the pair of particles, one entangled with each other. You throw one in, you get your choice to think about this particle being entangled with the charge distribution on the horizon, or more simply, with just the image charge on the interior. And there's some similarity here that you can think of this particle as, it certainly remains entangled with something. You can't destroy entanglement. This particle would either be thought of as being entangled with the degrees of freedom on the stretched horizon, analogously to the charges in the mirror, or you can think of it as being entangled with a holographic image on the inside. So,
Black shirt.
When we are talking about the interior of the black hole, can we really ignore the presence of the singularity? Of the singularity. There's a singularity there.
yeah,
And we ignore it. It's not.
yeah, we ignore it. For a sufficiently big black hole, okay, it's a very good question. So let me tell you what the usual answer would be. If you take a very, very big black hole, then the singularity is deep in the interior somewheres. Of course, this is a misleading picture, but it's good enough for our purposes right now. But if the black hole is sufficiently big, there's a region way out here, far from the singularity, where the singularity is just not important. So you could ask your questions about what happens to somebody who falls in, and restrict yourself to this region here, which has not been, where space is more or less flat, where the presence of the singularity is not a serious issue. When you get near the singularity, of course, everything that we know breaks down. So for a sufficiently big black hole, let's say a black hole like at the center of the biggest galaxies, 1 billion solar masses. 1 billion solar masses, somebody falling in would have about 20 minutes after passing the horizon, during which they were far enough from the singularity that they would not feel huge tidal forces, they would not feel anything serious. And you can frame all the questions about this region here. So, that's not to say the singularity is not important or not interesting, but the paradox can be formulated independently of the properties of the singularity.
Question. So the Hawking radiation is in the form of electron-positron pairs.
Mostly photons and gravitons.
Okay. So, and if that somehow carries the information from the interior of the black hole, can you do funny things by throwing the Hawking radiation into other black holes?
Even worse, you can do really funny things by throwing the Hawking radiation back into the original black hole.
Oh, right.
And this is what a lot of our debates are about, Gedanken experiments and infinite confusion about what happens.
So here there are three different uses, A, B, and this radiation.
Yeah.
And you're trying to say that they might.
There's A, B, the horizon degrees of freedom, and the radiation. See, here's my terminology. I call the horizon these things here. I call it H. And then B and H, this is the near horizon stuff near the black hole, form black hole. You see. Now, B is entangled with something. What on earth could B be entangled with? A. A and B are entangled. Alice and Bob. So I call this Alice and this Bob, this horizon, and this R. The maniacs, the Santa Barbarians, call this thing. They do call this B, but what do you call this thing?
B tilde.
B tilde. And this one out here? C. Okay, but they're all the same thing.
So my question is that, is there any way to think about a possibility where A and B are information basically the same? The way you're identifying A equal to RB, is there some kind of different proposal where A and B are?
No. I'm not saying it's wrong. I'm just saying there's no such proposal.
Yeah.
No. A is entangled with B. That's different than saying A is B.
Right, but I'm saying, if I, from a information theoretical point of view, two things could be the same. If they are spatially at different places, their relative entropy will be non-zero. Because SA, suppose you have just two A and B in the whole universe. You calculate if A and B were almost, because,
Yep.
for example, S of A is same as S of B, if it's a pure state.
S of A has to be equal to S of B. Right.
Right, so then,
That doesn't say A is B.
no, but I'm not saying they're the same, but in some, I don't know, some moral sense they could be same.
Well, in some, I don't know, I don't think this is a question of morality myself. Well, there is a question of morality here. B must have a monogamous entanglement, may not have a polygamous entanglement. But in any other moral sense, to say two things is entangled is a very deep relationship, but it's not quite the same as saying they're the same. It does say that anything you want to know about A, any measurement that you would like to make on A, you can find out the answer by doing an appropriate measurement on B. It makes A and B awfully closely related, but it's not quite the same as saying they're the same. Information theoretically.
Yeah, but I was thinking in this case, it could be that somehow A and B were somehow, then they can both be entangled with R. I don't know.
Yeah.
Okay, doesn't matter.
That's one possible way to think about it. The other possible way is to say that A is R. In either case, you do come up against, you really can't have A and B being, A and R, or for that matter, A and B, being two identical copies of the same thing. That's the no cloning theorem. So I neglected to say that. You might have said, okay, there's just another copy of A out here. No, you can't make copies of things quantum mechanically. That's a theorem.
Yes, that's all.
Would there be a condensed matter analog situation or something?
What could be more condensed than a black hole?
No. More.
That's a good question, and it would be lovely if we had some condensed matter analog for this that we could appeal to and look at. And I don't know any. It seems to me that these issues really do have to do with a combination of gravity and quantum mechanics. I don't know anybody who has a good condensed matter analogy for what happens in black hole physics, but that could be wrong. There is a condensed matter analogy for what happens for black holes. It's called the dumb hole. Dumb like deaf. That's because sound is replacing light. Some of you may know it. If you take a lake of water, flat, then you put a drain hole into the bottom of it so that the water or whatever the fluid happens to be drains out in such a way, so fast, that at some place the water exceeds the speed of sound. Then you have something which is in some ways similar to a black hole. If you pass that point, sound cannot get out. It creates Hawking radiation. And you could ask, can you manufacture the same kind of paradox? Well, not really, because if you ask what happens to the information that falls into such thing, it certainly doesn't get radiated back out in the Hawking radiation. It just goes down the drain, and you find it on the floor, of your cave underneath there. So there's no good analogy for this kind of holographic behavior. So I don't know one.
I think we have time for one more question.
This is for the biologist. I don't know physics. So it seems your problem is that you cannot entangle three-way.
Yeah.
But at the same time, you said earlier that you can, entanglement is a graded quantity.
Yes,
I don't
yes,
understand why
yes,
you
yes,
can't
yes,
share
sure.
your entanglement.
Good. You can have a state in which B is partially entangled with A and partially entangled with R. That won't do it. It just won't do it. For practical purposes, for the purposes of the discussion, it's very useful to think of the empty space as having essentially maximal entanglement between B and A. Now, that's not exact, but it does, and that's, of course, one of the first things people think about when they hear this paradox. They say, oh, well, these are not maximally entangled. And these are not going to be maximally entangled. Maybe we can squeeze through. Turns out not to be the case. Turns out not to be the case. There's a more refined version of this called the, what's it called? The inequality.
Strong subadditivity.
Strong subadditivity. That does a more refined job of it.
Before we thank Lenny, Marty, is there any, do you have any announcements for the group here? No? Is there anything this afternoon in terms of wine and cheese?
Yes, there is a wine and cheese.
There's a wine and
We were
cheese?
told there is. We're not supplying it. We were told there is.
Okay, so that'll be at 5. Yeah. In the common area. Okay. All right. Thank you, Lenny.
Thank you.